Chapter 2: Data Models and Query Languages. The limits of my language mean the limits of my world. Ludwig Wittgenstein, Tractatus Logico-Philosophicus 1922. Data models are perhaps the most important part of developing software, because they have such a profound effect, not only on how the software is written, but also on how we think about the problem that we are solving. Most applications are built by layering one data model on top of another. For each layer, the key question is, how is it represented in terms of the next lower layer? For example, as an application developer, you look at the real world in which there are people, organizations, goods, actions, money flows, sensors, etc., and model it in terms of objects or data structures and APIs that manipulate those data structures. Those structures are often specific to your application. When you want to store those data structures, you express them in terms of a general-purpose data model, such as JSON or XML documents, tables in a relational database, or a graph model. The engineers who built your database software decided on a way of representing that JSON/XML/relational/graph data in terms of bytes in memory, on disk, or on a network. The representation may allow the data to be queried, searched, manipulated, and processed in various ways. On yet lower levels, hardware engineers have figured out how to represent bytes in terms of electrical currents, pulses of light, magnetic fields, and more. In a complex application, there may be more intermediary levels, such as APIs built upon APIs, but the basic idea is still the same. Each layer hides the complexity of the layers below it by providing a clean data model. These abstractions allow different groups of people, for example, the engineers at the database vendor and the application developers, using their database to work together effectively. There are many different kinds of data models, and every data model embodies assumptions about how it is going to be used. Some kinds of usage are easy and some are not supported. Some operations are fast and some perform badly. Some data transformations feel natural and some are awkward. It can take a lot of effort to master just one data model. Think how many books there are on relational data modeling. Building software is hard enough, even when working with just one data model and without worrying about its inner workings. But since the data model has such a profound effect on what the software above it can and can't do, it's important to choose one that is appropriate to the application. In this chapter, we will look at a range of general-purpose data models for data storage and querying. Point 2 in the preceding list. In particular, we will compare the relational model, the document model, and a few graph-based data models. We will also look at various query languages and compare their use cases. In Chapter 3, we will discuss how storage engines work, that is, how these data models are actually implemented. Point 3 in the list. Relational model versus document model. The best-known data model today is probably that of SQL, based on the relational model proposed by Edgar Codd in 1970. Data is organized into relations called tables in SQL, where each relation is an unordered collection of tuples rows in SQL. The relational model was a theoretical proposal, and many people at the time doubted whether it could be implemented efficiently. However, by the mid-1980s, Relational Database Management Systems (RDBMs) and SQL had become the tools of choice for most people who needed to store and query data with some kind of regular structure. The dominance of relational databases has lasted around 25-30 years, an eternity in computing history. The roots of relational databases lie in business data processing, which was performed on mainframe computers in the 1960s and 70s. The use cases appear mundane from today's perspective. Typically transaction processing, entering sales or banking transactions, airline reservations, stock keeping in warehouses, and batch processing, customer invoicing, payroll, reporting. Other databases at that time forced application developers to think a lot about the internal representation of the data in the database. The goal of the relational model was to hide that implementation detail behind a cleaner interface. Over the years, there have been many competing approaches to data storage and querying. In the 1970s and early 1980s, the network model and the hierarchical model were the main alternatives, but the relational model came to dominate them. Object databases came and went again in the late 1980s and early 1990s. XML databases appeared in the early 2000s, but have only seen niche adoption. Each competitor to the relational model generated a lot of hype in its time, but it never lasted. As computers became vastly more powerful and networked, they started being used for increasingly diverse purposes. And remarkably, relational databases turned out to generalize very well, beyond their original scope of business data processing, to a broad variety of use cases. Much of what you see on the web today is still powered by relational databases, be it online publishing, discussion, social networking, e-commerce, games, software as a service productivity applications, or much more. The birth of NoSQL. Now, in the 2010s, NoSQL is the latest attempt to overthrow the relational model's dominance. The name NoSQL is unfortunate, since it doesn't actually refer to any particular technology. It was originally intended simply as a catchy Twitter hashtag for a meetup on open source, distributed, non-relational databases in 2009. Nevertheless, the term struck a nerve and quickly spread through the web startup community and beyond. A number of interesting database systems are now associated with the #NoSQL hashtag, and it has been retroactively reinterpreted as not only SQL. There are several driving forces behind the adoption of NoSQL databases, including a need for greater scalability than relational databases can easily achieve, including very large datasets or very high write throughput, a widespread preference for free and open source software over commercial database products, specialized query operations that are not well supported by the relational model, frustration with the restrictiveness of relational schemas, and a desire for a more dynamic and expressive data model. Different applications have different requirements, and the best choice of technology for one use case may well be different from the best choice for another use case. It therefore seems likely that in the foreseeable future, relational databases will continue to be used alongside a broad variety of non-relational data stores, an idea that is sometimes called polyglot persistence. The object-relational mismatch. Most application development today is done in object-oriented programming languages, which leads to a common criticism of the SQL data model. If data is stored in relational tables, an awkward translation layer is required between the objects in the I, a term borrowed from electronics. Every electric circuit has a certain impedance resistance to alternating current on its inputs and outputs. When you connect one circuit's output to another one's input, the power transfer across the connection is maximized if the output and input impedances of the two circuits match. An impedance mismatch can lead to signal reflections and other troubles. Application code and the database model of tables, rows, and columns. The disconnect between the models is sometimes called an impedance mismatch. Object-Relational Mapping ORM frameworks like Active Record and Hibernate reduce the amount of boilerplate code required for this translation layer, but they can't completely hide the differences between the two models. For example, Figure 2-1 illustrates how a resume, a LinkedIn profile, could be expressed in a relational schema. The profile as a whole can be identified by a unique identifier, user ID. Fields like first name and last name appear exactly once per user, so they can be modeled as columns on the user's table. However, most people have had more than one job in their career positions, and people may have varying numbers of periods of education and any number of pieces of contact information. There is a one-to-many relationship from the user to these items, which can be represented in various ways. Figure 2-1, representing a LinkedIn profile using a relational schema. Photo of Bill Gates courtesy of Wikimedia Commons. Ricardo Stuckert, again Gibraltar. In the traditional SQL model prior to SQL:1999, the most common normalized representation is to put positions, education, and contact information in separate tables, with a foreign key reference to the user's table, as in Figure 2-1. Later versions of the SQL standard added support for structured data types and XML data. This allowed multi-valued data to be stored within a single row, with support for querying and indexing inside those documents. These features are supported to varying degrees by Oracle, IBM DB2, MS SQL Server, and PostgreSQL. A JSON data type is also supported by several databases, including IBM DB2, MySQL, and PostgreSQL. A third option is to encode jobs, education, and contact info as a JSON or XML document, store it on a text column in the database, and let the application interpret its structure and content. In this setup, you typically cannot use the database to query for values inside that encoded column. For data structure like a resume, which is mostly a self-contained document, a JSON representation can be quite appropriate. See example 2-1. JSON has the appeal of being much simpler than XML. Document-oriented databases like MongoDB, RethinkDB, CouchDB, and Espresso support this data model. Example 2-1, representing a LinkedIn profile as a JSON document. Figure 2-2, one-to-many relationships forming a tree structure. Some developers feel that the JSON model reduces the impedance mismatch between the application code and the storage layer. However, as we shall see in Chapter 4, there are also problems with JSON as a data encoding format. The lack of a schema is often cited as an advantage. We will discuss this in schema flexibility in the document model on page 39. The JSON representation has better locality than the multi-table schema in Figure 2-1. If you want to fetch a profile in the relational example, you need to either perform multiple queries, query each table by user ID, or perform a messy multi-way join between the user's table and its subordinate tables. In the JSON representation, all the relevant information is in one place, and one query is sufficient. The one-to-many relationships, from the user profile to the user's positions, educational history, and contact information imply a tree structure in the data, and the JSON representation makes this tree structure explicit. See Figure 2-2. Literature on the relational model distinguishes several different normal forms, but the distinctions are of little practical interest. As a rule of thumb, if you're duplicating values that could be stored in just one place, the schema is not normalized.